In this tutorial, we're going to focus on survival analysis. So what is survival analysis? Well, survival analysis actually refers to different statistical techniques that can be used to investigate how long it takes for an event to occur. So how did it get the name survival analysis? Well, the term survival analysis comes from the medical and health studies that predicted survival time. So the name's fairly intuitive here. Now, we can of course focus on survival analysis and apply it to different types of contexts. For example, we can apply it to organizational research to understand how long before someone leaves an organization. So we could focus on voluntary turnover. So if someone at their own discretion or volition decides to leave an organization, perhaps for another job or for other reasons, again, that would be an example of quitting or voluntary turnover. Or we could perhaps focus on involuntary turnover. So those people who it's not their own choice to leave the organization, but rather they're asked to leave. In other words, they're terminated, fired, or separated from the organization. Now, we'll be focusing on today two different types statistical techniques for carrying out survival analysis in R. Now, again, survival analysis is actually a bit of a misnomer because it's a broader family of analyses that we're actually referring to here. And so we'll focus on today how to conduct a Kaplan-Meier analysis, which is an example of a non-parametric method for survival analysis. And this means that it does not have the same distributional assumptions as a parametric method, such as normality and things like that you might be familiar with. Now, the Kaplan-Meier analysis is going to allow us to estimate the standard error and the confidence interval of the survival rate at each time interval of interest, as well as across the entire study. Now, this is going to help us account for and understand uncertainty that's owing to sampling error. Now, using this type of analysis, we can also understand how independent groups of cases, such as people from different race or ethnicity groups, for example, differ with respect to their survival rates for whatever the event is we're interested in understanding or predicting. And we can also help to understand, too, if those different independent groups experience different overall survival curves or trajectories. Now, the Kaplan-Meier analysis is really an example of what we could call a descriptive approach to survival analysis, in that it is really we're trying to describe how the survival process unfolds. We can add a categorical covariate, which is really what we're talking about if we, for example, added a race variable that's categorical in nature. That would be an example of trying to then understand essentially what is the predictor of different groups' survival rates. Now, as part of the Kaplan-Meier analysis in this tutorial today, we're going to learn how to create an abbreviated version of what is referred to as a life table. And I'll explain that a little bit later on in more detail. But the basic idea is that we are constructing a table where we can look at different time intervals and see what is the cumulative survival rate or survival probability for cases within each one of those intervals. Now, the second type of statistical technique that we're going to focus on today is what's called the Cox proportional hazards model, and sometimes it goes by simply Cox regression. And this is referred to as what's called a semi-parametric method. And it's referred to semi-parametric because it makes a distributional assumption about the covariates in the model and their relation to the hazard, but it does not make a distributional assumption about the hazard function itself. And we'll explain more about what the hazard function is when we get to that point. Now, this analysis is going to allow us to investigate not only categorical covariates that we can add to the model, or in other words, categorical predictor variables, but we can also add in continuous variables as well. And so we'll learn more about that as well as understand how to interpret the hazard rate and so forth as part of that analysis or that particular approach to survival analysis. Now, another thing that we're going to focus on today is what's called censoring. So due to normal data acquisition processes, we often collected data at a specific point in time. That is, we have this time interval, essentially a start of our study and an end of our study, or rather the start of our data collection and the end of our data collection. And this is going to really have an effect in terms of which data might be considered censored. Okay? So, for example, for some individuals, the event in question, let's say it's voluntary turnover for this example here. So let's assume that for some individuals, the event in question will not have occurred, at least in the context of the study. So it means that if we're interested in voluntary turnover, there's going to be some people that by the end of the study, by the final time point or data collection date, they have not yet experienced the event in question. These are going to be people who are considered censored or referred to as censored cases. And that's actually an example of what's called right censoring, which is a very common type of censoring that occurs within survival analyses. Now, alternatively, other individuals may have experienced another event and may have left the study early before the endpoint, but it was not due to the event, the focal event in question, which for this example is voluntary turnover. And so those would be examples of people who are right-censored as well. Maybe they left because they were fired or for some other reason, but it wasn't their own choice. They didn't choose to quit the organization, which would be an example of voluntary turnover. Okay, so those what I've just described are examples of what's called, as I mentioned, right censoring. Now I should note though, there's also left censoring and interval censoring, and we're not going to focus on those today because they tend to be specifically, or in particular left censoring, tends to be less of an issue or less commonly incurred or experienced within an organizational research setting. However, interval censored cases could occur, and this essentially means that the event in question happened between 2 points in time, but we don't have a precise date. That would be an example of interval censoring, but we're not going to focus on that today because often we do have at least fairly precise organizational records in terms of things like voluntary turnover. We usually have a termination date or a turnover date of some kind where we know more or less within a day or so when that person officially left the organization. So what are the statistical assumptions for the Kaplan-Meier analysis and the Cox proportional hazards model? Well, in terms of the statistical assumptions, they're not, because these are not parametric methods. Well, the Cox proportional hazard model is a semi-parametric method, so it does have some parametric characteristics as I described before, but it's not a fully parametric method. And the Kaplan-Meier analysis is a non-parametric method, meaning it doesn't make any distributional assumptions. Now, that's going to affect that we will have fewer statistical assumptions than maybe you typically are familiar with other types of parametric methods that you might have already learned how to do, such as OLS or ordinary least squares linear regression or something like that. Now, given that these are examples that we're going to be focusing on today of non-parametric and semi-parametric methods, so many of those statistical assumptions, again, are not going to be a focus here that we'd be commonly familiar with parametric methods. However, when we do apply regression-based approaches to survival analysis, such as the Cox proportional hazards model, there are some advantages to meeting some of these common regression-based techniques in order to actually improve statistical power. Okay? So for the Cox proportional hazards model, while it is a semi-parametric method that we're focusing on here, there could be some advantages if we do try to meet the assumptions of a fully parametric method. Okay? But we're not going to focus on those today, and we're not going to investigate these because, again, these methods tend to have the assumption that they are in part non-parametric in nature. Okay, so let's move on to the initial steps here for this tutorial. The first thing that we're going to do is let's set our working directory. Okay, and that's going to be the location on your computer or wherever you're looking for that has the data file in question. The data file we're going to be using for this tutorial is called survival with a capital S, and it's a .csv file. And I'm going to use the setwd function, and I know that that file is saved in my H drive and my R workshop folder. It's going to likely be a different folder for you on your computer, so just find that folder or specify the path here within the setwd function and run. And as you can see here, I've set the working directory. If you want to do it manually or via drop-down menus, you can use session, set working directory, and choose directory, and then you can click on the folder and generate this, this exact function for your particular computer and where you've saved that file. You can generate, it'll appear in the console as it did here, and then you can paste it up here. Next thing we're going to do is we're going to read in the data, and I'm going to put make this an annotation, but you may need to do this if you've never done this before, but I am going to note that you should have installed the reader package previously, and it's just READR, all lowercase. And so if you have not ever installed the reader package or you need to update it, then you would want to actually run this line of script here. I've actually recently installed the reader package, so it should be up to date. And so I'm going to use just a function from it, and that is going to be the read_CSV function. And in order to access that function, I need to use the library function from base R, and I'm going to type in reader as the sole parenthetical argument so that I can actually check that function out and access it here. and access that, or really check that package out rather, and then access that reads_CSV function that I just mentioned. So I'll go ahead and run that. And the next thing I'm going to do is I'm going to read in the data. And I'm going to read in that survival.csv file that I mentioned earlier. And I'm going to come up with a name, an original name here for the data frame object. Let's just call it servdat for survival data brief. It's just going to be servdat, all lowercase, one word. And using the left-handed arrow operator, I'm going to assign the data that I read in using the read_CSV function from that reader package that we just accessed. And again, the name of the data file is survival with a capital S .csv, and this file is saved to this folder here within my H drive. And so you'll need to make sure that your working directory is set to where this file is actually located. Okay, so I just successfully read in the data there. The next thing that I'm going to do is I'm going to come over here to my global environment. You can see I have a lot of other things, other objects in my global environment here, and I can actually just clear these out here and then rerun that. Okay, so let's rerun that read_CSV function again. Okay, that's much better. Now I've just got the servdat data frame object that I read in. It's 701 observations, which in this case refers to 701 cases, and each case or observation is an individual person. So you can see we have a unique ID variable here, a unique identifier variable. We have a start date for each person, so this is when they started in the organization. We have their gender, race, their hourly pay. Let's assume that this is their last hourly pay rate that they received, and either before they left the organization or by the end of the study. And we also we have access to their pay satisfaction ratings, and let's assume that they were sent out a survey at some point. Maybe it was quarterly survey, and this is just the most recent level of pay satisfaction they had, either by the end of the survey or when they left the organization. And we also have access to what type of turnover, if at all, they experience. And so for this, let's assume that 0 means that they did not leave the organization within the time frame of the study. And let's say that 1 represents voluntary turnover, so they decided to leave the organization or they decided to quit. And let's say that 2 represents someone who involuntarily turned over, meaning that they were fired, for example. Now, for those people who did leave the organization before the study was completed, we have here, we have their actual turnover dates, and you can see these listed out here. And these were used in part, you're lucky here because here the length of service variable, so how long someone worked in the organization before either quitting or by the end of the study when it had completed, how long they'd been working in the organization to that point has already been calculated. And let's just assume that it's based on some future date after all these start dates and so forth. So this person worked 986 days, so the unit of measure here is days, before they quit, and they quit. So this would just be how many days are between January 14th, 2017 and this person's start date of May 4th, 2014, and that turns out to be 986 days. For people that did not leave the organization by the end of the study, it's just how many days they had worked by the end of the data collection or the end of the study itself. Okay, so those are our focal variables here. And the next thing that we're going to do is we're actually going to create what's called the censoring variable. So I described what censoring was a little bit earlier on, and so now we're actually going to create a separate variable that's going to indicate those people who were, in our case, we're focused on, were right censored. So this is going to be people who either were still working in the organization by the end of this study, or they are people who left the organization for some reason other than voluntary turnover. And so I'll make a note that we're really referring to right censoring here. So again, we're going to focus on the focal event being voluntary turnover here. And so anything that's other than voluntary turnover, if someone left the organization or they're still in the study, that's going to be considered right censored. So I already walked you through what the turnover variable has, the coding we're going to be using, which is 0, 1, 2, 0 for stayed in the organization through the duration of the study. 1 is they voluntary turned over, which is our focal event. So 1 is what we're trying to describe or predict the time until this event occurs of voluntary turnover. And 2 is that they left for involuntary reasons. They were involuntarily turned over from the organization or fired or something like that. So what we're going to do is we are going to essentially take that turnover variable and we are going to create a new variable that let's call it censored, and we are going to specify basically either you're a 0, meaning these are going to be the people that are still in the study by the time of the study's completion, so that's an example of right censoring, or the people who involuntarily left. Those are going to also be examples of right censoring, and we're going to refer to those cases. Those are going to be our right censored cases, and so we'll assign them a 0 value. So for the people that actually experience the event, these are going to be the people that we'll code as 1 here. Okay, so these are our non-censored cases. Okay, so to do that, let's use this type of operation here. We do our name of our data frame, which is served at. This is what we just read in and named earlier. We'll use the dollar sign to then attach a new variable we're about to create, which let's call this censored, all lowercase here for our censoring variable. And then we're going to put brackets in here. We're going to specify the same data frame that we did before, and then we're going to reference the turnover variable. And the reason we're going to do this is to create a logical operation here. We're going to say when turnover, that variable, is equal to 1, and so remember in R we use the double equal signs for the logical equal operator here. So when turnover is equal to 1, we're going to create in the new censored variable, all those people are going to receive a 1. Okay, so these are the people. 1 means that they experienced the event in question. So these people are not censored. Okay, we can go ahead and run that. So you might get a little error message here, or not an error message, but a warning message that says unknown or uninitialized column censored. It's fine, as you'll probably see when we go over here. We do now have this new column or variable, which is called censored, that we created. And you'll just note that those people who had, or rather voluntary turnover, they had experienced that within the study. So again, that's our focal event. They are now coded as 1 for censored here. But you'll see that there's NAs because we have not yet specified who those people are that are going to be censored, or specifically right censored. So how do we do that? Well, let's just copy the same notation here, except now let's say that those people who are actually going to be right censored are going to be those people for the turnover variable, where turnover is equal to 0, meaning they stayed throughout the duration of the study, they remained in the organization. And we'll then use the logical or, the straight vertical line here, to say, or those people, and I'll go ahead and copy this here, or those people for which the turnover variable was equal to 2. So these are the people who involuntarily turned over. They left or because they were fired, for example. Okay, so we're saying if the turnover variable is equal to 0 or if it was equal to 2, we're going to right censor those, and we're going to assign the 0 value to those cases for the new censored variable that we've created already. Okay, so let's go ahead and run that. Take a peek at our data frame object, and now you'll see that it's filled out here, where we can see that all the people with 0s now are right censored, meaning either they stayed in the organization throughout the duration of the study, they did not experience the focal event, or they did not experience the focal event but experienced some other event, such as involuntary turnover, that led them to leave the study before its culmination or the end of it. Okay, so now we have our censored variable, and this is going to be a good first step before we actually start specifying first our Kaplan-Meier analysis, and then later on we'll use it again when we get to the Cox proportional hazards model that we estimate. So now, just for fun, let's actually inspect the distribution of the length of service variable. Okay, and remember that stands for, or we use the acronym LOS for that, and it's all caps here in the data frame. So it's LOS, all caps, stands for length of service. Okay, so let's see just what the distribution is for that length of service for the entire data frame. Okay, so if we just look across everybody, by the end of the study, what was their length of service? And so some people, this means that they might have left earlier, and maybe they, depending on what their start date is, that's going to affect their length of service. And some people, this just means how long they'd worked by the end of the study, and they were still working in that organization by the end of the study. So those people who are, for example, right censored. Okay, so we'll do the same notation we did above, which is the name of the data frame served at, $, and we will put LOS, so length of service, as our focal variable. But let's throw this in parentheses, did this a little bit backwards here, and throw it into our histogram function, or just all lowercase HIST. This is the histogram function from base R. Click run. So here you can see that the length of service is relatively normally distributed, at least looking at the histogram here. Now, sometimes you might find for some survival data that actually you're going to see a positively skewed data, which means, or it's positively skewed distribution, meaning that you'll see that perhaps a lot of people experience the event in question early on, and then that tapers off into a long right tail. And perhaps for others, you might see a left skewed distribution where it takes people longer to experience event in question, but then it starts growing kind of exponentially for a while. So we can also drill down a little bit deeper too, and this is just mainly to kind of show you how to play around with this a bit if you're interested in doing some more inspection of length of service or any other variable if you're trying to look at specific groupings and looking at those histograms for a particular variable. Okay, so let's actually copy what we just created there, and I'll show you an example here. So let's say we want to inspect the distribution for the length of service for just those people who stayed in the organization. Okay, so those people, by the end of the study, they're still in our study, and they're still in our organization. So what we can do is we can nest the subset function, and I'll finish out the parenthesis here, within the histogram function, and we'll do a little bit different notation here. So first, as the first argument within the subset function, we'll specify the name of the data frame, and then we'll specify the name of a variable that we can subset by. So let's subset by the turnover variable, and when it's equal to 0, which would be those people who stayed in the organization. And then we come outside the parenthesis here, and we are now going to say that we're essentially refining the data frame, we've subset it here, and then we're doing the same thing. We're attaching the $sign here and the length of service variable here. So all we've done is essentially blown out this part in the previous function, and we've created this, a subset data frame within the histogram function. If we run that, we'll just get a subset of just those people who stayed in terms of their length of service. This also looks like a relatively normal distribution. Copy that. And let's also, just for fun, take a look at those people who voluntarily turned over. What was their length of service? So I'm just replacing the 0 with a 1 here. Remember, for turnover, 1 equals voluntary turnover. And we can see more or less a normal distribution again. Okay, so this is fairly normally distributed data here for the length of service variable, even when we look across these different levels of turnover too, and look at different groupings there as far as subsetting goes. Okay, so now let's do one of the specific types or statistical techniques of survival analysis we're going to focus on in this tutorial. We're going to start with the Kaplan-Meier analysis, and I'll just put CAM analysis for short here as another reference point. And as part of this, we're going to generate an abbreviated version of what's referred to as a life table. Now, to do that, we're first going to we're going to use actually a function from the survival package. It's survival all lowercase, so we're going to need to install a package. And so you likely haven't installed this already, so make sure you run this. It's going to be installed at packages, and within quotation marks as the sole parenthetical argument, survival all lowercase. I recently installed this, so I'm not going to run this, but most likely you'll need to install this. I'm going to use hashtag annotation, a $sign there to annotate that out so that R doesn't run it for me if I were to go back and run the entire script from start to finish. But I will use the library function because I have downloaded and installed this function recently. I'm going to use the library, or rather installed this package. I'm going to use the library function to access this package and its functions. So I'll run that. Looks like it was accessed with no problem. Okay, so the next thing that we're going to do is we're going to specify the Kaplan-Meier analysis model. And so what we're going to do is like we would with the LM function, the linear model function, and other functions where we specify models within R, we usually want to name the model object something. So I'm going to call this first model object KM for Kaplan-Meier underscore fit1. Okay, so this is KM fit1. This is the model object that we're about to specify here, and that we're about to fit here. So we'll use the left-handed arrow operator here to assign the results of the what's called the serve fit function from the survival package in just a second here. So the name of the function is survfit, S-U-R-V-F-I-T, all one word and all lowercase, and that's from the survival package. And as the first argument, we are going to specify the model. We're actually going to specify what's called a null model or an empty model, which means that we do not have any covariates in this model. Because remember, as I mentioned earlier, Kaplan-Meier analysis will allow us to include a categorical covariate variable as a predictor in the model, because we can actually look at independent groups of cases and how their survival rates differ, as well as their overall survival curve or trajectory. So this is going to be perhaps a little bit unusual notation you might not be as familiar with, but we're going to apply what's called the serve function as a nested function within servfit, and that's serve with a capital S. And within the parentheses of the serve function, the first argument is going to be the time to event variable, which for us is our length of service variable. So length of service, or LOS, all caps, is our time to event variable. The second variable we specify the second argument we specify within the serve function is going to be that censored variable we created above. Remember, we created this variable and we called it censored all lowercase. We're going to enter this as the second argument. Okay. So this is going to specify our survival function there. And then we'll use the tilde symbol here. And to the right of the tilde, we are going to put 1. And this is just going to specify that we don't have any covariates and we just want a null model here. Okay, so we're just requesting a null model here, or that's what we're specifying. Okay, so I'm going to put a comma there. So this whole section right here is our first argument of the servfit function. The second argument, we're going to do data equals and the name of the data frame object from which these variables LOS and censored come from, which is servdat. That's our data frame object. And our third argument, separating all the arguments with commas, is going to be type equals and Kaplan-Meier. Make sure you spell it correctly there. Kaplan-Meier, no space, and a hyphen between Kaplan and Meier. This specifies that we are going to run a Kaplan-Meier analysis. Okay, so the next thing that we're going to do is let's run that function, the servfit function, and assign the results of it to the km underscore fit function. So we've just fit the model here to our data. And the next thing we can do is let's just use the print function from base R. We don't need to use this. We could just highlight and run the name of our object here, but let's, for fun, print function with the name of our object km underscore fit1, the model fit object we just specified, and run that. And down here in your console, you will see that it reiterates what you called up in terms of the formula or the model that you specified, as well as the data and the type of analysis and so forth. But what we're really interested here is this information. So this is the survival information for the entire sample, okay? So we're not looking at any specific time interval here. It's for the entire span of the study. What is the survival rate? And so here you can see we have 701 cases, which should look familiar here, or observations in our data frame. 463 under events refers to how many people experience the focal event, which remember we specified as voluntary turnover. So how many people experience the focal event, which in our censored variable was coded as 1, okay? Before the end of the study, so before the data collection in the study had terminated. And what is the median length of service or length of time before someone experienced that event of voluntary turnover? Well, is 1,059 days. Okay, so 1,059 days post start date is the median number of days that people worked before experiencing voluntary turnover or quitting the organization. Now we also have the 95% confidence interval. We have the lower limit and we have the upper limit for this. So the lower limit, and this is where the standard errors get applied to create the confidence interval. The lower limit is 1,022 days, and the upper 95% confidence interval limit is 1,095 days. So you can see that the median is our point estimate between these two limits here for the 95% confidence interval. So that gives us a nice bird's eye view of just the median number of days until people quit the organization within our study. Okay. The next thing we're going to do is we're going to summarize the Kaplan-Meier analysis results using what are going to be the default time intervals that the function provides for us. And we're also going to create a life table, and specifically an abbreviated life table from this. And I'll explain more, and it'll make a little bit more sense once we get our output what these default time intervals are. Okay, so to do that, we're just going to use the summary function from base R. You're probably very familiar with this function. The summary function, and we're just going to put the name of our model fit object, so km_fit1 that we specified above here. That's going to be the sole parenthetical argument in our summary function. So you get quite a bit of output here. And what you'll see is, again, you get reminded what your model is and what your function specifications were for the serve_fit function here above. But we get our life table down here as output. So now by default, this function begins each new time interval, which you see under the time column here. And this function by default begins each new time interval at the time at which a new event, or rather at the time at which the event occurs, okay? So you're humming along and the event hasn't occurred until day 73. So this indicates right here that the first time interval is from 0 days to 73 days. And so this is the day at which someone, the first people experienced that event of voluntary turnover. And it looks like people experienced the event, 12 people experienced the event 73 days after they started in the organization. So when their length of service was 73 days, 12 people voluntarily turned over, okay? And then you'll see that then a number of days pass, and then we get to day 110, and now here one person experienced the event, so under number who experienced the event here, experienced the event 110 days into their tenure or their length of service at the organization. Okay, so that's the default approach, and I'll show you if you want to set more theoretically relevant or organizationally relevant time intervals and specific ranges of days. I'll show you how to do that in a second. But first, let's start by really breaking apart this life table here and understanding what it's giving to us. So I already mentioned that this time column is our time interval here. It specifies here the different time intervals that have defaulted for this particular function. Now the in.risk column here corresponds to the average number of individuals at risk for the event for this time interval in question. Okay, so for this time interval here, 682, we have 682 people were at risk for experiencing voluntary turnover during that interval. The in.event column, as I alluded to before or mentioned before, this is the number of people who experienced the event in question. So in this case, voluntary turnover within that time interval. And we then have the survival column here, which is often what we're really interested in many ways. And this is going to contain the proportion of individuals who survived past or through the time interval in question. And it's really commonly referred to as the cumulative survival rate here. Okay, and sometimes you'll see this right here represented by the notation S sub I, okay, where I refers to the specific time interval. So let's play around with this here. So what you'll see here is the cumulative survival rate here for this time interval. So we have everybody, this would be from 70 or greater than 73 days to 110 days here. that we see that the survival rate is 0.98. So it's about 98% of people were still living at this point. So surviving, which in this case, they had yet to turn over. So they had yet to experience the event in question here. And then here's the standard error. And then here we have the 95% upper and lower confidence interval for that particular survival rate here. Okay, so you can see the confidence interval ranges from 0.9715 to 0.9915. It comes from, we apply the summary function from base R to an object that was created using the survFit function from the survival package. Now, as I alluded to before, we can also set our own time intervals that we'd like to specify. Okay, so let's go ahead and do that. So we're going to summarize the Kaplan-Meier analysis results. And we're going to be doing this by pre-specified time intervals. And we're going to create a life table as well. So for this, let's apply the summary function once more. And we're going to, as the first argument, so now we'll have multiple arguments, it's going to be the name of the model fit object, so km underscore fit1, comma. And then we're going to add a second argument, which is times equals, and here's where we specify our confidence, or rather, this is where we specify our time intervals that we're interested in. Okay, and so what we're going to do is let's actually set the time intervals to, it's going to be 0 to 30 days, 30 to 60 days, 90 days, and then we are going to do 30, every time interval after 90 days is going to be a 90-day interval. So essentially quarterly intervals after the first 90 days. And we're going to do that for an additional, let's say, 30 times. Okay, so 30 additional 90-day intervals after those first 90 days. So what's the notation going to look like? Well, using the C function from base R, the combine function, we're going to first say we want the first interval is going to be up to 30 days. The next interval is going to be up to 60 days, or between 30 and 60 here. And then we're going to have 90 days, okay? But as I mentioned, we are going to do quarterly or 90-day intervals for 30 more times, okay? So we'll do it up to 90 days, and then we're using the asterisk to indicate that now we're going to essentially create multiples of this. So 30 different times, so 30 different repetitions of this 90-day interval, and you'll see this play out here in the life table when we run this. So let's go ahead and run this. Okay, so here you should see this looking pretty familiar. So we specified up 0 to 30 days here, 0 to 60 days, 0 to 90 days, and then you see it's 90-day increments all the way here. And here it just truncates, I believe the default is if it gets to the end here and there's no more people left, then it just ends prematurely there. Okay? So here we can see this is just a different way to slice and dice, and you can see that no one experiences the event. The cumulative survival rate for the first 60 days is 1 or 100%. So everybody survives. They don't experience voluntary turnover. But then things get more interesting when we get up to between 60 and 90 days, and then every 90-day increment or interval after that. Okay, so sometimes it's easier, and you'll see that we have the same columns in terms of standard error and the upper and lower limits of the 95% confidence interval as well. Sometimes it's easier to plot these things. So let's plot the cumulative survival rates, or you can think of these as probabilities too, survival rates. And we can do this really simply just using the plot function from base R. If we plug in that km underscore fit, the model fit object that we specified before, Kaplan-Meier Analysis model fit object. And you'll come over here to the window. And so here is our survival function here, or this is our cumulative survival rates over time. Okay. So here we can see there's 100% survival. That's the line there. But then when we start getting down here and there's no error, and this corresponds to there's the standard error is 0. And so our confidence interval is exactly our point estimate of 1 here. And you see that playing out in this object because you don't see the confidence interval represented by dotted lines here or dashed lines. And you can see the confidence interval is the dashed lines around these steps. So this is what each step represents one of the time intervals here. And you can see this repeated here all the way through the end of the study here. And so then you can see we get to a point where it stabilizes down here and we lose the last person, okay? Or we have one person, we lose the last person to voluntary turnover, okay? There's still other people left in our data who were censored, right? Censored, who stayed in the organization through the duration of the study. But the confidence interval gives you an idea of the error in around the cumulative survival rate here as you see it. Okay, so this is a cumulative survival rate. You see this, it takes this kind of this typical curve form here. Oh, and the x-axis here is the number of days from for the time to event. So this is our length of service here on the x-axis, and again, the rate or the probability is there on the y-axis. Now, I personally don't find that particular data visualization to be too aesthetically pleasing, and there's actually some other bells and whistles we could throw in there that can be a little bit more informative. So what we're going to do is let's kick things up a notch, and let's actually use what's called the ggservplot function that comes from the serve-miner package. So I'm going to assume that you haven't installed this package before, and it's called install. Well, you use the install.packages function, and as the parenthetical argument within quotation marks, it's just serve-miner. So serve-miner, all lowercase. And I have recently installed this, so I'm not going to do this, but you'll likely need to run this line and not put the hashtag or the pound sign before it to annotate it. You will definitely need to, and I know I definitely need to access this package within this session, and to do so, I'm going to use the library function. Type in the name serve-miner of that package so I can access that package and its functions. Just ran that. Okay, now I'm ready to use that ggservplot. So I'll say plot aesthetically pleasing version of plot from above. And so I'm going to use the ggservplot function. So it's ggservplot, no underscores, all lowercase. First argument is going to be the name of our model fit object, km_fit1. That should be looking familiar here. Second argument, data equals, and then our servdat, that's the name of our data frame object here. And then the next argument is going to be, and this is optional, but I'm going to say risk.table equals true, meaning that I want a risk table, and you'll see what that looks like in a second. And then I also want the confidence interval, so conf.int equals true. And I'll return here to the last argument. And let's do a minimalistic theme here. This package, as you can see down here, a required package, it's dependent on the ggplot2 data visualization package. And so let's take advantage of that and do ggtheme equals and theme underscore minimal. And this comes from the ggplot2 package. And we can just leave that empty here. So we don't need to put anything, the theme underscore minimal function there. Just leave that as is. And so let's go ahead and run that function. Took a second there, but now let's take a look here at what we have. So this should look familiar. This is the same cumulative survival rates over time here. And remember, time is length of service here, or time until event. Length of service until someone experiences voluntary turnover. You'll see that here it says strata, and this is referring to the singular of that would be stratum. So we haven't stratified the data yet in terms of creating independent groups of people, such as by race, for example, and we'll actually do that in the subsequent step. But in addition to the curve here, and you can see shaded the confidence intervals here, in addition to that, we also get the number at risk. So this is the table we requested by putting risk.table equals true. And this just tells us that at, you can see here, 0 days, we have 701 people, so everybody's at risk at that point. Okay, they could potentially voluntarily turn over at any time. Then we get to 500 days, and we have 610 people are at risk because people have turned over, and then 281, 15, and then we get to day 2,000 length of service or post-hire, number of days post-hire, and then by this point, everybody has experienced the event in terms of those people who would be experiencing that event, which is voluntary turnover. Okay, so again, you don't need to do this, but I do think it looks a lot nicer, and you do get that risk table. It's one advantage of using the ggserv plot function from the serve-miner package. Okay, so let's kick things up a notch once more by specifying a new Kaplan-Meier analysis model, and this time let's add a categorical covariate, in other words, a categorical predictor variable that we can use to specify the independent groups of cases to see how their survival rates vary across time. So to do so, let's actually just borrow from this script above. I'm going to copy this. So this is where we specified our KM analysis model, or Kaplan-Meier analysis model above. And I am just going to add to this annotation with a categorical covariate. And let's call this model KM_fit2, and I'll change that in the print function below here. So this is just our second KM model fit object here that we're specifying. Use the serve fit function from the survival package. We're going to keep the left hand, or the left side of the tilde the same. So this is our outcome essentially. This is our survival here. And the only thing we're going to change is to the right, we're going to specify a categorical covariate here. And this is going to be our race variable, which here we have race is equal to black, I believe Hispanic, Latino, and white. Okay, so there's three race groups here, three categories. It's a between subjects variable, meaning that each person only belongs to one of the groups. So that's what we need here as far as the categorical variable is concerned. Now, we can keep everything else the same in this function. So the data equals and the type equals are going to stay the same. So let's actually run this all together with the print function here. Remember, this will give us the overall view of survival information. And here, now this will look somewhat familiar. Remember before, actually it's probably truncated above here, but yeah, before we just got overall, when we did not have a categorical predictive variable, we were just running the null or the empty model. We just got overall information about the number of people in our sample, the number who experienced the event, and the median and the upper and lower 95% confidence interval. Here we see the same information, but it's broken down by category here. So for those people who have identify as being black in terms of their race, their information appears here in this line, and then those people who identify as Hispanic, Latino, and those people who identify as white, the final line there. And so you can see here's the sample sizes for each one of those independent groups. Number of people that experienced the event of voluntary turnover by the end of the study was 190 for the black individuals, 57 for the Hispanic Latino individuals, and 216 for the white individuals. And then we can see the median length of service, or time to event, time to voluntary turnover, for these different groups, and the confidence intervals as well around those point estimates. Okay, so the next thing, as before, we're going to summarize, and actually let me just borrow again from above here, these two lines where we use the summary function. And only thing I'm gonna change in these is from KM_fit1 to KM_fit2 to reference our new Kaplan-Meier analysis model fit object. And so let's first run a summary to get our life table here. And so now you'll see a difference too in terms of the life interval, our life table. Again, it's going to default in the same way that I described before when we just run the summary function by itself with the serve fit model fit object, which is KM_fit2 here. So the time intervals are by default, but notice now it's by independent groups. It's by the category of individuals whose race is black. Then we have Hispanic Latino, their life table, and the life table for the individuals who identify as white here. Okay, so we have that modeled there. And we can do the same thing as we did before, which was we can also come up with pre-specified time intervals. So I'm doing 30, 60, 90 days, and then every 90 days after that, using the summary function there. And so here we see that same notation. Again, it's broken down by race, okay? Because that's our categorical covariate here. All right, so the next thing that we're going to do is we're actually going to specify, we're going to create a similar data visualization to this one, except this time we're going to include the model fit object, the km_fit2, that has the categorical covariate in it. And to do so, we are going to go up here and again borrow this script from above where we use our ggservplot function from the serve_minor package. Come down and copy this here. I'm just going to shorten this up to a plot. And the only thing we're going to change here is km_fit1 to km_fit2. And everything else is going to stay the same here, except I do want to add in, actually, 2 additional arguments here, which is going to be the p-value equals true argument, as well as the p-val method equals true. And so what this is going to do is this is going to, behind the scenes, it will actually, this will not only plot our data, but it's also going to perform an analysis behind the scenes. And specifically, it's going to apply what's called the log rank test, which actually comes from a Cox proportional hazards model typically. And we're going to compare to see whether or not those cumulative survival rate trajectories or curves are significantly different between the different groups of the categorical covariate. Okay, in this case, that's race. So we'll be able to see, in other words, if the cumulative survival rate curves differ between those individuals who are white, black, or Hispanic Latino. And so that's what the p-value is doing. The p-val.method argument is saying, well, what method are you using? And I know by default this is going to be the log rank method here, but it's going to tell us that what it's using to actually do that test. When we get to Cox proportional hazards regression, I'll show you there's actually a few different tests that we can use to compare these. Okay? All right. And you'll see what I mean in a second. So let's run this. It takes a second to run. Get a little bit of a warning message here. Nothing to worry about. It's not an error message, but it's just warning us that something may change in future versions of ggplot2. Okay, so let's take a look here at our plot. And now you see the strata. This refers to the different, now we have 3 different stratums. So we have 3 different groups, in other words. We have the black individuals, the Hispanic Latino individuals, and the white individuals. So red, green, and blue, respectively. And we see those cumulative survival rate curves represented here. So it does look like there's a little bit of separation, especially like you do see some, at least descriptively, observationally, it looks like we can see some differences, but the question is, would we treat these as statistically significant differences? Well, according to the log rank test, remember we requested a significance test, a p-value in other words, to see whether or not these cumulative survival rates are different from one another. We see the p-value here is 0.073, which is greater than our conventional 0.05 alpha level, our cutoff that we typically use. So we'd say here that these cumulative survival rates don't seem to differ between the levels of the categorical covariate variable, which in this case they don't seem to differ between the different race groups here, these independent groups. One thing you will note though is down here, we have our risk table that we had requested before, but now we have the risk table separated by the different groupings, the independent groupings of employees, which correspond to our categorical covariate race variable that we added to the model here. But you'd interpret it in the same way. Okay, so that's how we can run a Kaplan-Meier analysis, and that is how we can also not only run the Kaplan-Meier analysis, but also create a life table as part of it. And as you saw here, using the ggservplot function, we can create something even a little bit more narrow, which is a risk table as well. So moving on, let's estimate Cox proportional hazards. I'll put pH here just for short. So for proportional hazards, just abbreviate that as pH, which is fairly common notation, and model. And remember, this is also sometimes referred to as a Cox regression model too. So you might hear either thing. So we are going to use from the survival package, we're going to use the Cox pH function to specify the Cox proportional hazards model. And so to do so, let's come up like we did with the Kaplan-Meier analysis, and as we usually do, let's come up with a model fit object name, and let's call it Cox underscore fit, regression reg1, okay? So we'll just call this Cox underscore reg1. You can call it whatever you want, but that's what I'm going to call it. It's fairly descriptive. And use the left-handed arrow operator to assign what we're about to specify here with the Cox pH function, and that's Cox pH all lowercase. So Cox pH all lowercase, no underscore. And it's going to be very similar notation. In fact, the same notation, because what we'll start off here is let's actually estimate a Cox proportional hazards model in which we use a categorical predictor variable. So we'll get to see kind of with the ggplot, the ggserve plot function from above where we got the log rank test, we'll actually get to see how that's created here using the Cox proportional hazards model, where that comes from. Okay, so it's going to be, again, just like the Kaplan-Meier analysis, it's going to use the same notation for the survival function that we're going to use for this, and which is capital S URV, so capital S lowercase URV functions we did before. And so the first argument for the serve function is going to be our time to event variable, which for us is LOS, or length of service. The second argument is going to be the censored variable. Again, this is exactly what we did with the Kaplan-Meier analysis model that we specified above. Okay, so that is the left hand of our formula or equation here. We'll separate that with the tilde here, and then to the right we put in our categorical covariate here, and we'll just use race again because that's what we did with our Kaplan-Meier analysis above. And then as our second argument, let's do data equals and serve dat, which just indicates that the LOS, censored, and race variables all come from the serve dat data frame object, which is this one here. Okay, so let's run that. And here we're actually just going to jump straight on to the summary function, and as a sole parenthetical argument, we're just going to put our Cox regression or Cox proportional hazards model fit object of Cox underscore reg1 as the sole parenthetical argument. Run that. And now what you have here is you have the output for the Cox proportional hazards model. So it's kind of nice. You get the formula above here and what you specified in your Cox pH function. But you also get your sample size, which is 701. We know that already. 701 cases. And we already knew from the Kaplan-Meier analysis that 463 people experienced voluntary turnover, which is the focal event in question here, throughout the existence of the study, or the duration of the study. Okay, so the next thing that we're going to do is we're going to come down here and we're going to look at the table that has our coefficients in it. And you'll see that abbreviated as coef there. And so you'll see that each one of these coefficients has their exponentiated values, which is you take Euler's numbers. So e to this value is going to give you 1.19645, okay? And so that's just something to note there. And I believe the notation in R should be e to the, let's just copy this. Oh, yeah. It is not, I'll actually have to look that up. I forget off the top of my head what Euler's number is. So let me grab that. Right, the notation is exp for exponentiate here to get, so it's Euler's number, but you'll see it as e to the power of this coefficient. And so let's go ahead and paste this first coefficient in here, and we should get this value here. Oh, there's the notation right there. It's exp. So it already notes it in the table for you there. Should have looked at that a little bit more carefully. Run that, and you'll see that is 1.196451, which rounds to this, what we see here. Okay, so this is our coefficient. This is the standard error of the coefficient. And this right here is the z, is the Wald statistic value, okay, and its associated p-value here. Now, what you'll note is that behind the scenes here, because race is categorical and it has 3 levels, if it had just, because it has 3 levels, we actually, and it would do this too if it had just 2 levels too, but there's a dummy code that's taken place behind the scenes. And if you have a question about what dummy variables are, check out my tutorial called Hierarchical Linear Regression in R. I get into a little bit more about what dummy variables actually are and what they mean. Okay, so a little bit more background on them. But basically here, the reference group is just going to be alphabetical here, in the sense that because black comes before Hispanic, Latino, and white alphabetically, black becomes the reference group here. Okay, so what we're seeing here is we're comparing the Hispanic Latino group here, their survival rate essentially, to the black individuals, and the same with the white individuals here. We're comparing their survival rate to the black individuals. A little bit later on, I'll show you how you can actually change that reference group if you'd like to change it to something that's maybe more meaningful, and so forth and so on. So we actually don't see any differences between the different groups here when we compare them to the black reference group there. Again, this is a dummy code variable behind the scene, or several dummy code variables behind the scenes. And so you can see both of these p-values, which located here, is greater than 0.05, which is our conventional cutoff. So for that reason, because we don't see this p-value being less than 0.05, which is the conventional cutoff, we're not going to come down here. And here you see the exponentiated coefficient values here. We see these repeated here, as well as their reciprocal is provided here as well, and their upper and lower confidence interval. We're not going to interpret this because they're non-significant here. But what we will do in this particular example here is we will look at this bottom model level information, which will start with the concordance here. So what is the concordance? Well, it's actually an aggregate estimate of how well the model predicted individual people's experience of the event in terms of time. Okay, so how well did this model predict how long people were going to survive until the event, essentially, is what we're looking at here. So what happens behind the scenes here is that pairs of individuals are compared to determine whether the individual with the temporally earlier experience of the event is correctly predicted by the model. So if the model is accurate, the pair is considered to be concordant. Okay, so the overall concordance score is actually going to represent the proportion of pairs of individuals who experience of the event, which in our case, the event in question is voluntary turnover, whose experience of the event was accurately predicted. So a concordance value of 0.5 indicates that the model really does no better than chance. In other words, there's a 50-50 chance of correctly predicting which individuals incur the event, which individual incurs the event before the other. Now in our data, you can see here that the concordance is going to be 0.522, and the standard error for that is 0.014. And so 0.522 descriptively, that indicates that the race covariate in the model slightly improves the accuracy of our predictions, but actually not by too much here, okay? Not by too much more than flipping a coin, but it's better than nothing, okay? So now let's come down to these statistics here, these tests. We have the likelihood ratio test, which is sometimes just abbreviated LRT. We have the Wald test, and we have the log rank test down here. Now, the log rank test is what we saw before. So this is what was happening behind the scenes here when we were comparing the cumulative survival rates across the 3 different categories of race here. And so we'll see this is rounded. This is the same p-value that we see here that was done behind the scenes there. Now, it's really, you can use any 3 of these tests, the likelihood ratio test, the Wald test, or the log rank test. However, what I'd recommend using is that you are going to report the log rank test. And the reason that we're going to do it is that it tends to work a little bit better when we have smaller sample sizes, okay? These tests will be asymptotically equivalent to one another when assuming you have a large enough sample size. But to err on the side of kind of caution, let's just go with the log rank test and interpret this one by itself, okay? So what we're doing here is we're just seeing, really what we're doing with the log rank test is we are just indicating here that the model with the race covariate here does not perform significantly better than a model with no covariance. Okay, so this is just essentially, or it's not essentially, it's comparing the current model where we have one covariate here that happens to be categorical with a model in which we had no covariates. Okay, so I can actually show you here what this would look like if we just had an empty model. You don't have to follow along with this, but if you want to just visually watch me do this, let's replace race with 1. So we're just going to run a null model here. And everything else stays the same. And I'll actually just, so we don't overwrite the existing Cox_reg1 object, run this. Okay, so this is our empty model here. So there's not going to be any test of coefficients because there's no coefficients here. Okay, because we didn't put any covariates in this model. And we just get the overall information in terms of the sample size, and we can see that it's just the null model. This is what is being compared to. And so for the log likelihood ratio test, or the likelihood ratio test, this is what's being, the model we just looked at above is being compared to, okay, is this null model here. So that's what's happening behind the scenes. So now let's actually kick things up one more notch, and this time let's go back and I'm actually going to delete the null model we just created here. And I'm going to copy this Cox proportional hazards model we just specified above. Let's create a second model that we'll call Cox_reg2. So change the 1 to a 2 for those. And instead of just race, we're going to create a fuller model, is one way to say it, with 2 additional predictor variables or covariates. And this time we're going to include continuous covariates. So race was a categorical covariate. Now let's include the hourly pay rate for people as well as their pay satisfaction ratings. So let's take a peek here at what were those variables called. Okay, pay_hourly with a capital P and pay_sat with a capital P as well. So pay_hourly plus pay_sat. So now we have 3 variables in our model, and so we're actually, the model we just ran would actually be a nested model. It'd be nested within this model because it has the race covariate here as well as 2 additional covariates in our second model. So this is will ultimately become our full model here. All right, so let's go ahead and run this model. So let's take a look at the output of that function. And specifically of the model that we just specified, which is a Cox proportional hazards model with, again, a categorical covariate and 2 continuous covariates as well. So you'll see as we get all of the model, we get the function information, the arguments that we specified. This will look familiar here. But note here that our sample size is now 663 instead of 701, and we get this little note here that says 38 observations were deleted to missingness, due to missingness. And this specifically indicates that this was due to list-wise missingness. And I can tell you, I know from the data that if you were to look at it, that the pay satisfaction variable, 38 cases or 38 individuals in this data set, or this data frame, were missing their pay satisfaction value. And that could be for a variety of reasons. Maybe they just didn't participate in one of the surveys. Maybe it was voluntary or something like that, or their data were lost. Okay? So that's why we see that drop of 38 cases from 701 to 663. And then we see of the 663, 445 experienced the event in question, which is, of course, voluntary turnover. First 2 lines of the coefficients table will look familiar from the previous table we looked at above, and these are just the dummy variables where we're comparing Hispanic Latino risk for experiencing the event to the white individual, to the black individuals, and then the white individuals' risk for experiencing the event in question, which is voluntary turnover. We're comparing that to the black individuals as well. And again, this isn't surprising. We don't see that those are significant because we did not see that in the table or in the model above when we had just race as a covariate. Okay. Now we do see when we look at our 2 continuous covariates that we added to the model, we do see that hourly pay here is statistically associated with the risk for experiencing voluntary turnover. And we see that's a negative association. So what that means is that the higher your hourly pay, or the higher an individual's hourly pay was, the less risk they had for experiencing voluntary turnover within the confines or the time period of the study in question. And so we know that this is statistically significant because the p-value is less than the conventional alpha value of 0.05, which is the cutoff value we typically use. Okay, so given that the hourly pay covariate here, continuous covariate, is significantly associated with risk for experiencing the event in question, let's now go down to the next table, which is where we have our hazard ratios, which our hazard ratio is just this value here, just exponentiated. And so it's going to be 0.8961 here. And so how do you interpret this? Well, the way that I would suggest interpreting it is copy this value and do 1 minus that value. So 1 minus 0.8961. Okay. And so if we do that, we can interpret the hazard ratio as this. And that is that the risk of an individual voluntarily turning over, or in other words, the risk of an individual experiencing the focal event, is going to decrease by about, let's say, 10.4%, if we round that, for every additional dollar in hourly pay that that individual actually earned. Okay, so that's kind of informative there, that we get an idea of the magnitude of how much this risk is going to be decreased or reduced by each increase in terms of each dollar in terms of the amount of hourly pay that they're receiving. Okay. All right, so what about this next column here where we see minus coefficient? This is actually, we're talking about the reciprocal here. Okay, so here we've just done, this is the reciprocal of this value here. And so how do we calculate that? Well, it calculates it for us, but the way that we do that is, if we just wanted to do it ourselves, is 1 divided by that value. And so you'll see that's about the same. So 1.1159 rounds to 1.1160. And so this just gives us another lens with which to interpret this same finding. So we could say things a little bit different here. So when we focus on this reciprocal being about, let's say, 1.116, this is going to indicate that the risk of staying in the organization, so in other words, the risk of not experiencing the event in question, is going to increase 1.116 times for every additional dollar earned in hourly pay. So it's really up to you. If you want to report the hazard ratio in its original form or the reciprocal of the hazard ratio, it's completely up to you, and it's up to the context, not up to the context, but think about the context and think about what's going to be most appropriate or easiest to explain to people in that context. And then also, it's good to report the 95% confidence interval around that hazard ratio, which you get right here. Okay. Now, if you do report the reciprocal, I also recommend reporting the coefficient or the hazard ratio in its original form as well. And the reason for that is the 95% confidence interval relates to the hazard ratio and not directly to the reciprocal of the hazard ratio, which it appears there. Okay. So one thing to consider too is that you can think of this as an equation, and so we could actually write out this equation, and we could compute the overall risk, and well, specifically it'd be the log overall risk for people based on these coefficients and different values we could plug in for these variables here. Okay, but do keep in mind that these variables are not grain centered here, so the reference is going to be we're going to be comparing if you were to specify a model like that and interpret it, or specify an equation like that and interpret it, you would be comparing it to an hourly pay rate of 0, which is probably illegal, if not extremely unlikely, and a pay satisfaction level of 0, which I don't even think the pay satisfaction variable, let's see here, its lowest value is 2 here, and it probably, let's say, theoretically, it could have been 1, okay? So that's something to consider too, is if you do decide to write out this in equation form, what your actual reference groups are going to be here, okay? And what you're actually referencing. So for fun, I'll just show you like a quick example of what I'm talking about here. So let's call this log overall risk, this is kind of long here, but let's actually make an equation here that we can use to specify our the results of our Cox regression or Cox proportional hazards model here. So we could actually calculate this out for specific individuals who have certain characteristics. Okay, so the first thing that we'll see from our output here, we're going to use just the raw coefficients there, is that let's say that is for the first dummy variable of the race Hispanic Latino compared to the black group. Let's say that that coefficient is about 1.21 and times, and let's create a variable that we'll specify subsequently. Let's call this race HL, just for race Hispanic Latino, indicating that that's what we're comparing to the black group there. And then we will do actually plus minus 0.044. And so this is the coefficient here with some rounding, times, we'll specify a variable subsequently. Let's call this race W for white, and then plus, looks like negative 0.10, or it's about negative 0.110. And that is going to be associated with, let's just pay hourly, so pH. We'll create a variable there. And so we're just specifying this equation right now. And then the last coefficient is 0.141 times PS for pay satisfaction. Okay, so this is a equation we've just set up here that we can try to estimate. We can estimate the log overall risk for a specific individual. And so I'll actually just cancel out, since we have plus, adding together or adding on a negative value there, drop out the plus signs there, just simplifying things a little bit, and making this into the following equation. So this is the equation, and we can actually run this, but you'll see that it can't find these race variables yet. So how do we specify those? Well, let's just assign some values to this and play around with this. So let's say that race HL, let's say that it's equal to 1, meaning that we're going to think of a hypothetical person who is Hispanic Latino. So that would mean they would have a 1 for the race HL variable because it's and 0 for that variable would indicate that it is not race Hispanic Latino. Okay? And then for race W or race white, there'd be 0 because the person is not does not identify as being white. They identify as being Hispanic Latino. So it's 1, 0. And then for the next variable, we called that PH, capital PH. And let's say that their pay rate is $16 an hour. Okay. And then for PS, let's say that their pay satisfaction level was 0.400. So here we've just specified, and again, if you need some greater understanding of how these dummy variables work, check out the hierarchical linear regression tutorial I have. But here we've just plugged in some hypothetical values for an individual who's Hispanic Latino, makes $16 an hour, and has a 4 on the 1 to 5 pay satisfaction scale. And so we're trying to figure out what is the log of their overall risk, the log overall risk of experiencing the event. Okay, so let's actually so now we've assigned those values to those objects. Let's run this equation, and then we can just print down here below and put in the results of the equation. The log overall risk is negative 1.075 here. Okay, and so this is going to be the log of their overall risk score for their survival time prior to experiencing the event. Okay, and that's, again, negative 1.075. And so now if we exponentiate that, we're going to arrive at the following. So if we exponentiate it, exp is the function for exponentiation. Put this object in the parentheses there and run that. And we get a value of 0.341. So this means that the overall risk of voluntarily turning over for this particular individual who is Hispanic Latino makes $16 an hour and got a 4 out of 5 on the pay satisfaction scale. So the risk of this person voluntarily turning over within this this time frame is 0.341. So this means that the individual is, if you take 1 minus 0.341 rather, that this individual is 65.9% less likely to quit when compared to an individual with scores of 0 on each of the covariates in the model. Okay, so scores on each one of these covariates or variables in the model. If these were equal to 0, this person has a is 65.9% less likely to quit. Now, that might sound really awesome, but keep in mind what this means here. So for our equation, an individual who earns 0 on the covariates is going to be someone who is black. So if they had 0 on these two variables here, it would mean that they're not Hispanic, Latino, not white, so therefore they identify as black. And it also means that they're earning $0 an hour, which is probably not legal. And it also means that they have a score of 0 on the pay satisfaction scale, but the pay satisfaction scale can range from 1 to 5, so it's not even a meaningful value. So if you run into something like this, what I would suggest doing is the following. And that is to specifically do this, and I'll do a little shortcut here just for the sake of time. I'm just going to copy and paste these in, and I'm going to explain what they mean here. So you might want to pause to get a better idea of what I've written out here. But what we can do is we can grand mean center the continuous variables. Okay, so that means the continuous variables being, let's ignore this here. We just created some kind of quick shorthands here, but continuous variables being pay hourly, pay satisfaction. And that's the first thing that we'll do. And so that way the reference group, if we grand mean center, is going to be the average. Okay, so 0 will be equal to the average for that variable after we grand mean center the variable. Because remember, with grand mean centering, we're just taking that each person's level. So let's say this person's hourly pay of 13.23, and we're subtracting the overall sample mean. So this is a grand mean centering, and the resulting value is going to be their grand mean centered value. And what that ends up doing is meaning that the average becomes 0. And so that's our reference point. So instead of comparing that person we just described to someone with making 0 pay, which would probably be illegal, we can compare them to someone who is making average pay. And same with the pay satisfaction variable. Instead of comparing them to someone who has a completely theoretically meaningless value on this scale of 0, when it's a 1 to 5 scale, we can instead say, well, how do they compare to someone who has an average score based on this sample from that particular average score on this variable here. Okay, and so here, check out if you want to learn more about grand mean centering here, I would recommend checking out my tutorial called Centering and Standardizing Variables in R, and I go over different ways in which you can do this. But basically what I'm doing here is I'm just specifying that I want to center the hourly pay variable, and I'm creating a new variable called C underscore pay underscore hourly, and I'm doing the same thing for the pay satisfaction. So I'm creating new variables here. So I'll run these. And we can also, as I mentioned or alluded to before, by default, the reference group, when we have a categorical variable that is of type factor, so here we have Black, Hispanic, Latino, and white. We can actually change that so that the default is going to be a different reference group. So it's not alphabetically going to be the first group that is alphabetical, which would be the Black group. We could change it to something else. So let's change it to Hispanic, Latino. Let's make that the reference group, okay? So what we'll do here is we are going to use the factor function from base R, and as the first parenthetical argument, we just specify the name of the data frame, $, and then the categorical variable, which is race here. And then our second argument, we specify the levels, and then using the C function or combine function from base R, we put the order in which we want these levels. And so you put your reference group first. So now we've reordered this, so it's Hispanic Latino is our reference group because it comes first there. And I'm just creating a new variable here that I call HL underscore race that I'm attaching to the served at data frame object we've already been working from. And it just means I'm just signifying Hispanic Latino underscore race just means that HL Hispanic Latino is now our reference group. So we'll run this. You can see these are getting added to our data frame object here. Okay. All right. And now let's run, this is just the exact same model that we specified before, but now I'm plugging in these new variables that are the grand mean centered continuous variables and the reordered factor variable for the categorical variable here. So it has a new reference group, and I'm just calling this Cox_reg3. And so watch what happens here. Okay, so now we have, you'll see that the significance tests are not going to change here. Okay, it's still, that part of the interpretation stays the same. And we can see that our hazard ratio is not going to change either. But what is going to change is the actual coefficient values here that we plug into the equation. So let's grab this example that I was pulling here. Okay, so we're going to need to, now that we've copied and pasted what we were working with above here, now we need to adapt this based on our new findings here, now that we've input the new reference group for the race variable, and we've also grand mean centered the two continuous variables there. And so the first thing that we're going to need to do is we're going to need to reflect the fact that now the dummy variables, because Hispanic Latino group is the reference group, let's change race HL for Hispanic Latino to race B and replace that in our formula down here below. Keep race white the same, but just remember that it's the Hispanic Latino reference group. And for the focal individual, remember we're interested in an individual who is Hispanic Latino, which means they would have 0 for the race black dummy variable and the race white dummy variable, because if they have 0 on both of those, by default, it means that they are the reference group. Okay. Now, the next thing that we need to do is we need to take into consideration, well, okay, what is the hourly pay? But remember, with our hourly pay this time, we grand mean centered the variable, which means that we need to grand mean center this value of $16, which this is how much this Hispanic Latino person made this hypothetical person that we're going to plug into our equation here. Okay, so how do we do that? Well, we can calculate this by doing 16 minus and then the mean function from base R, and then serve dat underscore pay hourly. Technically, what we'd want to do, it'd increase more steps, is we'd actually want to subset this first and subset it down just to the 663 people who didn't have missing data. And so these are the people that ultimately are included in our model, but this will get us close enough probably, okay? So, and we know there's not any missing data on this variable, but we know that the next one will have missing data, which is the pay satisfaction variable. And so NA_RM equals true says to just drop those people with missing data, okay? And so if we do 16 minus that, if we type in pH here to see what that object is, now we'll see that that person has a score of 1.89 or so on this grand mean centered variable, which is equivalent to $16 an hour, because now remember the reference point is now, or the average is going to be our 0 value on that scale. And the average is this value here, so we can just run this, is $14 an hour and 11 cents. Okay, and we can do the same thing for pay satisfaction to convert this over here. Just change the variable name there and run. And we see that pay satisfaction of 4 out of 5 on the original scale, for the grand mean scale, it becomes 0.32. So both of this value here means that this person has an above average pay satisfaction rating. And again, because this value is positive, and because this value for the hourly pay variable is positive, it means that they have above average pay, okay? All right, so the next thing we're gonna need to do is plug in the new coefficients. And so you'll see here, the coefficient for the race black dummy variable is going to be negative 1.21, okay, plus negative 0.165, which can just be minus 0.165 for the dummy variable for the white dummy variable. And then plus minus 0.110, okay? So that's going to stay the same. And then also this coefficient will see this stay the same, because even when if we just do a simple transformation like a grand mean centering, it's not going to affect the slopes or the coefficients of our continuous variables. Okay, those are going to stay the same. So let's now run Let's run all of this together. So now we can see what the log of our overall risk is. Let's print log overall risk is going to be negative 1.62 here. Okay, so this all looks right. So the next thing that we'll do is we will, if we want to actually exponentiate using the exp function, we can plug in the log of our overall risk value there as the sole parenthetical argument, and you'll see that it is 0.850, let's say. Okay, so now that we have taken into consideration what we just did with the grand mean centering and the fact that we have changed the reference point and all that kind of stuff, we can now say that this individual is overall risk is going to be 0.850, okay? And if we do 1 minus 0.850, we get about 0.15, so let's say 15%. So this individual is 15% less likely to quit when compared to individuals with scores of 0 on each of the covariates in the model. So in other words, when compared to individuals who are Hispanic Latino, earn average hourly pay, and have average levels of pay satisfaction, okay? So now this value is more meaningful for us, okay? This is something that we can actually grab onto because it's referencing an average hourly pay, referencing average pay satisfaction, and so forth, okay? Finally, the last thing that we're going to do here is we are going to, I'll show you how to do nested model comparisons. So we're going to ignore, it doesn't really matter that we grand mean centered and all that kind of stuff here. We're just going to do a nested model comparison of the first Cox proportional hazards model we ran, which is Cox underscore reg 1, where we just had the categorical covariate of race. And then we're going to compare it with the full model, which had race plus hourly pay and pay satisfaction. That was Cox underscore reg 2. To do so, we're going to end up using the ANOVA function. This is similar to what you would do with if you had a linear model, ordinary least squares linear model in R, you would use the ANOVA function. But what we do need to consider is that, remember, the first model here, with only race as a categorical variable, because there was complete data on all variables here, there were 701 people in this sample, okay? However, for the next model, Cox underscore reg 2, remember that paysat variable, we found out that there was 38 people had missing data, so list-wise deletion resulted in a overall sample, or resulting sample of 663. So in order to compare the models, we need to make sure we're comparing models with the same number of variables in those models, okay? So the way that we'll do that is we will need to actually apply some, we'll apply actually a function, and this is something that I recommend using the drop underscore NA function from the tidier package, which is part of the tidyverse universe of packages. So I have recently done this, but you'll so I don't need to run this line right here where I've done install.packages and then tidier as the sole parenthetical argument within quotation marks. So you'll probably need to run that. I'm not going to run it, so I'm going to annotate it out there. But I am going to run the library function here with tidier, the name of the package as the sole parenthetical argument, and run that. Okay, and again, we're going to use the drop NA function. And what we're going to do is we're going to actually nest this within our previous functions that we created above. So I'm going to copy the Cox PH functions and the models that we created above. And let's nest these here. Delete the summaries. We don't need those at the moment. Okay, so what are we going to do? Well, we are going to, within the data function here, or the data argument rather, this is where we're going to apply drop NA, which is a function from the tidier package here. And it basically goes through and it drops those cases, it listwise deletes those cases that have missing data, either on the whole data frame or on certain variables that we're going to specify. And we're going to specify certain variables here. Okay, so our first argument is going to be the name of the data frame. And then the remaining arguments are just going to be the variables that we wish to drop anybody who has missing data on these. Okay, so it's going to be length of service, LOS, censored, race. It's any variable that's in our model, essentially. Or that's what it is. Is pay underscore hourly and pay underscore satisfaction. So that should be everything there. So we can run that. And so this is where you're going to see the change here. So watch this. We run this, and I'm just going to run the summary function down here and just put Cox underscore reg 1. So we've overwritten the previous Cox function. And so remember before it had 701 cases for the complete sample. Now it has 663. So now it's going to match this second data frame here. So or the second function here in the results. We don't need to actually do the drop NA here, but to be on the safe side, this is good practice just to make sure that you're going to be comparing, that you'll have the same sample sizes and the same cases in each. Okay, so I'm just pasting in what we had above there. So again, we did drop NA, and these variables were the ones from the full model here, okay, even though they didn't appear in the nested model. All right, so we can run this now. And we will know if we do summary down here in our console and Cox, reg 2. We already knew this was going to be 663. Okay, so we've just not relied on the Cox pH function to listwise delete based on the missing data for the pay satisfaction variable. We just preemptively did that here for the function using the drop underscore NA function from the tidier package. So the last thing that we do is we just do the ANOVA function, and this is how we can do our nested model comparisons. And so we just put in the model object names. So Cox underscore reg 1 is the first argument, and Cox underscore reg 2 is the second argument, and we run that. And now what you see is that we can actually do a nested model comparison, or this is what we have done. And so what you'll find down here is that the chi-square test, which is what you see right here, here's the chi-square value, degrees of freedom. The associated p-value is less than 0.05, so that indicates that the full model with all the covariates included, which were race, pay hourly, pay satisfaction, it fits the data significantly better than the smaller nested model that only had the categorical variable of race in it. Okay, so this is a specific nested model comparison here. Now, going up above, one thing that we didn't wrap up with the second regression model, this is our full model, this is the Cox underscore regression 2 model here, is the model fit information, the model comparison information. So the concordance, we actually see that, remember the concordance was like 0.52 when we just had race in the model. When we added, and I'm just looking at the output here, the summary Cox underscore reg 2 output, when we added the pay hourly and pay satisfaction, we see that the concordance actually increased by 0.03, so 0.03. And then remember, we're just going to use the log rank test. And now we see the log rank test, it is statistically significant. So the p-value is less than 0.05. And so this just indicates that this model, our Cox reg 2 model, fit the data significantly better than a null model where you did not have any covariates in the model. Okay, so this is just backtracking a bit and looking at what we could have interpreted up here in the output. We focus on the coefficients here, but this is just revisiting that once more. Okay. All right, well, that wraps up the tutorial on survival analysis.